Thank you very much for joining this session, the IoT at Enel. I'm very excited to be here this afternoon with you in order to share the results of a very interesting project that was delivered in Italy as part in the IoT space. My name is Federico Senese. I'm part of AWS Professional Service Organization, and as part of my job mission, I closely work with customers that are willing to implement innovative solutions on AWS Cloud. And I'm very excited today to be here with my friend Ignacio Berenguer from Enel to deliver this session. Thank you, Ignacio.
Okay. Hello. Good afternoon, everybody. Thank you for being here today. So let's look a little bit at the agenda that we have to share with you this afternoon. So first of all, we are going to start explaining a little bit who is Enel, what do we do, and why IoT is interesting for us. Then we are going to share with you the rationale why we choose AWS as the foundation for our Enel IoT platform. And then we will go to the details on what we did in this project. What is the platform that we built? And we are going to explain that with some scenario, some use cases, and some practical demo. And Federico, of course, will explain the details of the architecture. Okay, so let's get started. Let's see who is Enel. So Enel is a multinational energy company and one of the world's leading electricity and gas integrated operators. So we are present in the energy generation business. We have a installed capacity of 83 gigawatts. We are also for sure in the electricity and gas distribution business. We operate a network of 2.1 million kilometers. And we serve 65 million customers across the world. Okay? We are present in 31 countries across 4 continents. We are more or less 62,000 employees. So probably now you're thinking, okay, but this is a big company, utility company, energy generation, energy distribution. So it does sound very conventional, very 20th century-like. So why do these guys need IoT? And we need IoT precisely because the mission of my company is expressed by the concept of open power. And open power means that we really want to change the world of energy. Because open power means that we are opening energy access to more people around the world, in new countries, but not only, to people that previously did not have access in a convenient way to energy. Probably people that did not have access to an electricity distribution network. We are also opening the world of energy to new technologies for more sustainable energy generation and distribution. Here we are focusing especially on renewable sources and smart grids. We are also opening new ways for people to manage energy, building new processes that meet people's real need, that allow them to use energy in a much more efficient way, especially using smart meters and digitalization. And we are also opening new uses of energy. Here, we are very focused on electric transportation and connectivity. So now, you start to get the picture. We are not talking about our conventional business. We are betting the future of my company on innovation, on digital transformation. We are talking about the smart grids, distributed generation, probably generation in small distribution units. We are talking about the smart meters. We are talking about electric transportation. And in order to do this, we really need IoT, because we really need to be closer to our customers. We need to get data from our customer in real time, precisely, and data that we can act upon and we can develop insights in order to allow our customers to use energy in a very different way. And this is what we are doing. We are using IoT in order to face the challenges that are presented to us when building new solutions. So for example, for residential customers, what we did is use AWS IoT to build a connected home solution that provides services for home automation, for energy management, for security, for safety, and for assisted living. For our industrial customers, we are building energy management systems that will allow them to use energy in a more efficient way. And for our own industrial installations, we are improving the performance of our processes using IoT in areas such as predictive maintenance, materials management, logistics, health and safety. Okay, so this is about my company, Enel, and why we choose AWS as the foundation for our IoT platform. First of all, for us was a strategic choice. We already had an IT strategy, cloud first, and AWS is our partner, our strategic partner on this. So for us, choosing AWS IoT for the foundation of our platform was very aligned to this strategy. Then time to market. Consider that this is a connected home solution. We were able to design and build it in 6 months. So for us, using these kind of services really means developing a solution in a very good time to market. Future-proof. When we built this connected home solution in 2016, we did a very basic use of the AWS IoT. Today, we are able to improve this solution, incorporating computing on the edge, device management, video streaming. And for us, being able to leverage the evolution of the AWS IoT in our solutions is very important. And then for sure, scalability and manageability. Our platform is completely serverless, so for us, it's very easy to scale, it's very easy to manage. So let's go and let's start with the part of the architecture. The platform is used for all kinds of solutions, industrial customers, retail customers, our industrial installations. But in order to illustrate the architecture, we are going to follow a very simple scenario, which is the smart home scenario, okay? Very basic one. So here we have a household, okay, a retail customer, and this retail customer has our solution, which is composed of an IoT gateway. In the demo, we are going to use a Technicolor IoT gateway, which is the gateway that we use in building the IoT platform. And for sure, this gateway is able to connect to the different services in the cloud, AWS services in the cloud. Okay? This IoT gateway is also able to connect to some devices on the customer house. But most importantly, this IoT gateway is able to execute logic, to execute business logic in an edge computing environment. And we will see that in the architecture. As a sensor, we are going to have this sensor. This is a motion sensor. Let's imagine that it's only able to detect one event, movement. And we have this other sensor, which is a smart plug, okay? European smart plug, okay? So this smart plug is only able to switch on and switch off. And what we want to build as a business logic is very simple. When motion is detected, a smart plug is switched on. But because this is edge computing, this should run even if we don't have internet connectivity. And we are going to explain how we did that and how we are going to use that capability in the future. So now I'm going to pass the floor to Federico to explain what is the architecture of the Enel IoT platform.
Oh, thank you, Ignacio, for this very interesting background about the IoT experience at Enel. So as part of the technical discussion about the underlying architecture that was designed and implemented together with Enel, I will start with a very high-level architectural diagram that describes the main components and the main layers in which the solution can be decomposed, and then we will go into details about the different layers. So as Ignacio mentioned, this solution includes physical devices that are deployed in a specific operating environment. So if we consider, for instance, the residential use case, the user will be dealing with devices like smart plug, motion sensors, cameras that are typically deployed within a specific home environment. These devices are typically also constrained in terms of computational powers, in terms of networking capabilities. So these devices require a gateway in order to communicate to AWS Cloud. So the gateway will have the role to integrate the different devices according to the radio protocols that these devices are able to communicate with the gateway. And the gateway will be able, let's say, to make, let's say, usage of the data for local computing, for computing at the edge, as well as to forward this data to the cloud as appropriate according to the specific use case. As soon as the data is in the cloud, different kind of processing can happen according to the use case. We can have, for instance, data being stored in a kind of persistent storage in order to enable application to do analytics, or we can have this data being transferred to external application, for instance, in order to trigger different business logic in platforms that are outside the IoT architecture itself. What is also relevant to say is that the overall platform provides APIs that are exposed to external applications that need to integrate with the IoT architecture itself. So these are basically the three main components in which we can decompose the architecture. Now let's have a closer look to the different services that have been used in order to implement the IoT architecture as part of the Enel MVP project. So as soon as a gateway with all the devices are activated, we have some specific provisioning workflows that are basically aimed to make the gateways and the associated device being part of the platform. So all the activation, provisioning, and also the decommissioning workflows are managed by Lambda functions that are executed in AWS Cloud and strictly interact with AWS IoT Device Registry and AWS Greengrass for gateway and device provisioning. So as soon as a gateway and associated device has been activated, we can have basically data being captured and being executed locally. So we have basically the computing at the edge operating on the gateway, and this is basically supported by AWS Greengrass that provides a local execution environment for Lambda functions executing locally on the gateway. So we can have all the data being sent by the devices executing locally and in order to have computation logic at the edge. According to the use case, as I mentioned before, these data are transferred to AWS IoT. So we have the AWS IoT endpoint providing an MQTT endpoint where the gateway can send the message to. So according to the specific use case, we can have messages being transferred directly over MQTT topics, or we can have a device shadow document being updated by Greengrass. And here we are leveraging a very powerful mechanism provided by Greengrass that allow, for instance, the shadow document synchronization between the local computing environment at the edge, the Greengrass itself, with the device shadow document that is exposed and maintained in the cloud. So when we have when the data reach the AWS IoT, we have IoT rules being executed as part of the IoT service that are able to make further processing logic on the data. As I mentioned before, with an IoT solution, the value is in the data itself. So it's, let's say, quite a straightforward solution to store this data into different storage services. So as part of the IoT architecture at Enel, the solution includes different kind of storage services ranging from DynamoDB to S3 to Elasticsearch in order to store the data and enable the application to make the best usage of this data according to the use case. Last but not least, the platform provides APIs. So as part of the IoT architecture API, there are specific API for command and control of the devices that have been deployed. So using this API, for instance, an external application can perform action on the device, like turn on or turn off a smart plug, or even can be sent some specific commands to the gateway itself for system management operation. What is also interesting is that we have API that can simplify the integration with third-party application. So for instance, let's assume that we have all the data stored as part of Elasticsearch. We can expose a simple API to external application to query data into Elasticsearch and provide this data in a more, let's say, simplified structure. And this basically be achieved by a specific API being deployed on the API gateway and backed by Lambda function. What is also interesting is that the platform itself has also the capability to execute business rules at the edge. And this is one of the use cases that we'll be presenting shortly. And all the business rule configuration is achieved using a specific API resource being exposed by the API gateway and being implemented by Lambda function associated to the specific API. Okay, so basically this is a summary of the IoT architecture at Enel. So in order to, let's say, to make you become more familiar with this platform, we have selected the two main use cases that we would like to introduce to you in terms of user story, and also supported by a recorded demo. And then we will go through the specific details of the use case from a more technical perspective.
We are going to show today is IoT gateway activation. Consider that we are in a consumer scenario, okay? But this use case is very common to all the IoT solutions, because when you deliver an IoT gateway, what you want to have is that, let's say, the IoT gateway activation is unattended. In the retail scenario, what is happening is that the gateway, let's say, is manufactured and is shipped to the customer in a box together with the other devices in the kit. And this customer doesn't know anything about the IoT or the cloud or whatever, okay? So this customer just wants to unbox the gateway, power on the gateway, connect to the internet, and that should work. Behind, under the hood, a lot of processing is happening because this gateway needs to contact the IoT platform, needs to install a digital certificate, needs to create a Greengrass group, a lot of stuff that we are going to see shortly. No? But what we want to have is that this process is completely unattended. Okay? And after very few seconds or 2 minutes, after the customer connects the gateway, we should be able to manage the gateway, we should be able to start getting information from the gateway. So what we are going to demonstrate, and then Federico will explain in detail, is this kind of demo. So we have the gateway installed in a factory reset status, so just the firmware and the software that we put standard in the gateway. So the user is connecting this gateway to the internet, and we are going to switch the power on. In a normal customer situation, nothing will happen because the gateway is headless. No? We are going to open a console window so we can see what is the boot process of the gateway, what is happening, and we are going to open some logs so we can see what is happening in the gateway. Okay? And what we will see after, very few seconds after this is completed, is that in the AWS console, all the artifacts, the thing, the digital certificate, the policies, the Greengrass group, subscription, lambdas, etc. Everything is already deployed to the gateway. Okay, and at last, at the end of the demo, we are going to see that the gateway is already sending information to the IoT platform. Okay, so let's go to the demo. Okay. So the first step is connect the gateway to the internet and power on. This is the gateway, the technical gateway, and you see in the AWS console that we have only these things. We don't have a gateway which is in this number, ending in 48J. This is the console to the gateway, and when we switch on this gateway, we are going to start to see the boot up process. Okay, so this is basically a normal Linux boot up process. And when we are able, we are going to log to the gateway, and in order just to see some logs. And when this process is completed, we are going to go back to the AWS console and see what happened. Okay, so here we are logging to the gateway to activate some logs. So we see the messages from the orchestra at that point. Okay, this is the log of the device management agent doing activities on the gateway. And in this time, the gateway is downloading a digital certificate and executing some logic. So we are going to refresh the device registry in AWS IoT. And now what we are going to see is that the gateway is created in the device registry. Here you have it. So we have created a new thing in the device registry with all the information for this gateway. So we look into the details of the device registry. We have the environment prefix, we have the serial number, device ID, the maker, Technicolor, and the thing ARN. Okay, so this is a thing in the device registry. We're going to see that we already have a digital certificate associated to the gateway. Okay, so this is the digital certificate. And the policies needed to allow this device to do the activities that need to be done. Now we are going to go to Greengrass. So this Greengrass group was created as part of the auto-provisioning process. And the first thing that we see is that the deployment is successfully completed. So as part of the activation process, we deployed all the Greengrass configuration. These are the subscriptions, the minimal subscriptions that we need for this device to work between the cloud shadow and the local device shadow. At this point, as part of this Greengrass group, we have one core device, that is this gateway. We have no additional devices because we will pair additional sensors later. And we have deployed these 3 lambdas that are part of the Enel IoT platform. In the settings, we have configured some login configuration. And all this information is already, let's say, configured in the AWS console. Let's see if we are receiving data from the gateway. So we are going to create an MQTT subscription to one standard topic that we use for monitoring the gateways. Okay, this is like a heartbeat. Okay, so we are going to create this subscription to devices monitoring. And we are going to check because this is a heartbeat that is, let's say, sending a message every 30 seconds with some basic parameters about the health of the gateway. And there you are. So the customer only power on the device, and we are already getting information from the device in the IoT platform. This information is let's say, very basic, but as soon as we start pairing new devices, the motion sensor, the smart plugs, we are going to get more information. So Federico, please let us know how we did this.
Sure. Okay, good. Okay, so as Ignacio explained, the objective was basically to have a single push button action performed by the end user and all the auto-provisioning of the gateway happening automatically in the cloud. So now what I would like to explain more in detail are how this specific use case has been implemented and what kind of AWS service components have been used in order to make this happen. So as discussed when presenting the IoT architecture overview, what was anticipated is that all the communication from the gateway to AWS IoT happens over MQTT. So MQTT is the protocol of choice for this kind of communication. And as part of MQTT messages, all the gateway performed an authentication process over MQTT using TLS client authentication. So this means that the gateway is provisioned with a certificate, and in order to make this gateway be able to communicate with AWS IoT, this certificate should be received by AWS IoT and being activated. And this happened as part of the step 1 of the gateway provisioning process. And then once this certificate has been activated, then the gateway can start communicating with AWS IoT service in order to implement the gateway registration process. So what happens here is that all the entire provisioning workflow has been implemented by leveraging embedded capability provided by AWS IoT service for certificate activation. And then we have additional custom logic that has been implemented in order to adapt the certificate activation to the specific use case being implemented as part of the Enel project, as well as the gateway registration that should take care of the registration of the gateway into the different repository in which the gateway should operate. Now let's discuss more in detail the certificate activation and the gateway registration steps. So the gateway, when the gateway is plugged for the first time into the network, after the boot up process of the gateway will try to establish a connection to AWS IoT endpoint. And as part of this first connection, the gateway will attempt to authenticate using its own certificate. This certificate is recognized by the AWS IoT endpoint as a valid certificate because this certificate has been issued by a custom certification authority that was pre-configured within the AWS IoT account in which the solution has been deployed. So there is basically a match between the certificate being sent by the gateway and the certification authority issuing this certificate that is already being configured in the AWS IoT account. And basically this action will put the certificate into a pending activation state, and this state basically will trigger a Lambda function that is responsible to perform the certificate activation. And as a result of the outcome of the Lambda function, we have the certificate moving from the pending activation state to an active state with some specific policies being associated to this certificate in order to allow the gateway to perform the registration process. What is interesting is that all this process is supported by a feature provided by AWS IoT that is named just-in-time registration. That is one of the core capabilities of AWS IoT that simplified a lot the implementation of this specific use case. What is also interesting is the gateway registration process. So now we have the gateway certificate being into an active state. This basically enables the gateway to exchange information with the platform. So the very first message that the gateway will be sending to the platform is basically a registration request. So the gateway basically using MQTT will post a message over a specific registration topic, contain all the relevant information to let this gateway being registered as part of the platform. So and as a part of this use case, we have an IoT rule that is basically sending messages over the registration topic. So when a valid message has been received on this topic, the IoT rule basically will trigger a Lambda function that is responsible to implement the gateway registration workflow. As part of this workflow, we have different steps that aims to register the gateway into the different service components that are managing the gateway state in the cloud. So more specifically, we have the gateway being registered as a thing, as part of the AWS IoT Device Registry. And this is, let's say, quite straightforward. What is also interesting is that the gateway is part of a Greengrass group. So there is a Greengrass group being associated to the gateway, where the gateway is the core device. So as shown in the demo, all the artifacts belonging to Greengrass are created on the fly as part of the gateway registration process. So there is no pre-provisioning of AWS Greengrass group. Everything is created when required, so as part of the gateway registration process. Last but not least, we have also the pre-provisioning, the provisioning of resources into AWS S3 in order to allow the gateway to store device-specific data into S3 when required, as part of other use case that involves basically sending data to the cloud. So what is basically interesting about the gateway registration process? The gateway registration process itself is quite straightforward because includes, let's say, a well-known set of actions that should be performed as part of the gateway registration that are summarized here. What is also interesting is that each of these actions involves the interaction with a different service or component inside AWS cloud. And given basically the complexity that we can have as part of the gateway registration, each of these steps may individually fail. So what we have implemented basically as part of the gateway registration process is the ability basically to revert the system into a consistent state. So in case that any of the steps of the gateway registration process fails, we have a rollback procedure that aim basically to revert the system back into a consistent state where the gateway basically has not been registered, but its certificate has been activated. So let's assume basically that we have create the thing in the IoT registry, we have applied the security policies, we have configured S3, and we have a failure when creating the Greengrass group for any specific reason. So as part of the rollback process will attempt basically to deregister the gateway from the different services. As part of the rollback process, we have basically the attempt to remove the Greengrass group. So the Greengrass group does not exist. So this step will be skipped. Then the rollback procedure will go through the removal of the resources being created on S3. So the resources were created and then will be deleted. Then we have basically the removal of all the security policy being activated to the gateway certificate. And then we are deleting the thing from the device registry. So the rollback basically aims to keep the system into a consistent state, being the registration process an all or nothing process. In terms of technical challenges, this scenario was interesting for two main parts. The first one is related to the security part in terms of custom certification authority. So as mentioned, all the certificates are issued by a custom certification authority that has been configured into the AWS account hosting the solution. But this solution, as you can imagine, will be deployed across different business units and across multiple staging environments. And as part of the AWS IoT requirement, the same certification authority cannot be deployed more than once into a single region. So as part of the solution, basically what we have planned for is to use multiple certification authorities in order to accommodate the needs to have multiple business units deploying this solution and leveraging different staging environments. So basically this specific constraint led the requirement to manage multiple certification authorities as part of the overall solution. And the second part is related to the gateway registration process that involves multiple steps that may individually fail. So as part of the Lambda implementation basically was designed, Lambda was designed in a way basically to incorporate retry logic as much as possible in order to retry a step that failed wherever possible. And if this retry logic is not sufficient in order to keep the registration process till the end, then we are ensuring the consistency by including a specific rollback procedure for the entire gateway registration process. Good.
Okay, so let's move to the about edge computing. So what we want is what we described when we were looking at the scenario. We want to be able to define a rule. This is a business logic that has to be defined on the gateway. And this rule execution for the demo that we are going to see is very simple. When motion is detected in the motion sensor, a command is going to be sent to the smart plug to switch it on. Okay? So let's look at the demo. So in the demo, what we are going to see is, first of all, the rule definition using an API. So we are going to use Postman for defining this API. We already have the IoT gateway with all the devices connected, etc. And this is the device shadow of the motion sensor. And what we are going to do is to use Postman to call an API that would put that rule on the gateway. This is the API that we are calling. So we are putting this in the actions, the thing ID of the smart plug, and in the trigger, we have the thing ID of the motion sensor. So we send the rule, and now we are going to see that the rule is persisted in the device shadow. And because the device shadow in the cloud is synced with the local device shadow in the Greengrass core, this rule is now persisted in the IoT gateway. So now we are going to see what happens when we, let's say, detect some motion in the motion sensor. So we are going to uncover the motion sensor, which is in that box. Now the motion is detected, and you see that the lamp is switched on. Okay? So the rule was executed. In this case, the gateway was connected to the internet. Okay? So now we are going to see what will happen if we disconnect the gateway to the internet, because the rule is executed in Greengrass, so everything should work in the same way. So let's put everything in the normal situation, and let's see what happens when we disconnect the gateway from the internet. So we're going to unplug the internet cable, and we are going to do the same. We are going to uncover the motion sensor, so we detect motion. Okay, so there you go. The rule was executed on Greengrass, okay, without cloud connectivity. So, please, Federico, let us know how we build this.
Sure. Okay, so as Ignacio explained, as part of the real execution on the edge, there are two main steps that should be accomplished. The first one is the real configuration, and the second part is the real execution. So as part of the real configuration, we have basically an API being exposed by the API gateway and backed by a Lambda function. And this API is basically exposed to an external application that is responsible to configure the rule to be executed on a specific gateway, involving different devices that are associated to that gateway. So this rule basically this API will expose all the capability to create a rule, to modify an existing rule, or delete a rule, involving multiple devices that are connected to a specific gateway. And DynamoDB is used as main repository for the rule configuration. Then we have, of course, the AWS IoT service that is basically used as a mean in order to propagate this rule to the Greengrass for a local execution at the edge. And as part of the rule execution, we have basically different devices being part of the same Greengrass group. And we have Lambda functions executing inside the Greengrass that are responsible for the rule execution. Now let's go more in detail on how this specific part of this use case have been implemented. Let's look at the rule configuration. So we have an API being exposed by the API gateway, and this API is composed by different resources supporting the different operations that involves the rules. We have a Lambda function that is associated to this API that basically will persist the rules into a DynamoDB table. And when we have any modification affecting a rule, we have a second Lambda function that is associated to Dynamo using DynamoDB streams feature in order to update this rule as part of the IoT Device Shadow document of all the devices that are involved by the rule. This device shadow modification basically will trigger a device shadow update on the edge by leveraging the specific capability provided by Greengrass to keep the device shadow document being synchronized between the local execution environment on the edge and the device shadow document in the cloud. So we have been talking about the device shadow document, and here what we have is a concrete example of a rule definition being configured for the scenario that was demonstrated before. So in that scenario, basically we have a single rule, rule 1, that basically involves two different devices. We have one device, the device 1, that is a motion sensor that acts as a trigger for this scenario. And when basically its attribute motion detected equals to true, basically this condition basically will make the rule to be triggered, and the action of this rule will be executed against the devices listed into the action section of the rule, where we have a single device in this specific example, that is the device 2, that is basically a smart plug that will be basically powered on when a motion is detected. So as part of this rule configuration, basically we have tried to use as much as possible the embedded capability provided by Greengrass in order to keep the device shadow document being synchronized, as well as the Dynamo Stream capability in order to propagate data from DynamoDB to the AWS IoT Device Shadow document using a Lambda function. Okay, now let's have a closer look to the rule execution. So now we have the rule being configured as part of DynamoDB, and we have also the rule being reflected into the device shadow documents of all the devices being involved by specific rule configuration. Now let's have a look at what happens on Greengrass. So Greengrass, the two devices are part of a Greengrass group configuration. So this means that a Lambda running on a Greengrass core can basically interact with these two devices that are Greengrass-aware devices. So when we have any modification in the device 1 that comply to the rule configuration, meaning that in this specific case a motion is detected, we have a Lambda function that is responsible for the rule execution that will look through the rule configuration of what is basically the action that should be triggered. So this Lambda function basically will act on the device shadow document for the device 2, the smart plug, in order to power it on. So this Lambda function basically will operate on the IoT shadow document in order to sense what kind of triggering action are happening on the device 1. And according to this action, according to this triggering, an action will be executed on the device 2 as part of the rule configuration. And this is basically what we have seen as part of the video demo. We have had some triggering action being detected on the motion sensor and an action being performed on the smart plug according to the rule configuration. What is also interesting is that this scenario can also run in a disconnected way, because we have basically Greengrass being self-sufficient for Lambda execution even without a connection to the cloud, because the Lambda execution is locally performed, as well as we have the device shadow document being available as part of the Greengrass core runtime. In a more complex scenario, we can have also rules that can be configured in order to have as an action a service being configured in the cloud. So for this specific scenario, the solution includes the ability for a rule to publish a message over an MQTT topic, where we can include a specific IoT rule that will be responsible to execute the action in the cloud. And for auditing perspective, all the rule executions are audited as part of a DynamoDB table. So we have information about all the rules being executed on a Greengrass at the edge, also being logged into DynamoDB for auditing perspective. So this is basically the main description of the scenario. What I would also like to share with you are the technical challenges that we faced when designing and implementing this scenario. So first of all, this scenario basically involves the implementation of a custom rule engine that is based on the paradigm if this then that. This is a well-known paradigm that was taken and implemented on top of Greengrass by using the different solution components that we have been discussing so far. And in terms of implementation, this custom engine has been designed in order to manage simple cases. So cases that involve a limited number of devices as triggers or actions. For more complex cases involving a wide number of devices in terms of triggering of triggers or in terms of a device that should receive an action, we also foresee the requirement to optimize the Lambda being responsible for rule execution in order to optimize the execution in order, let's say, to avoid and to be safe in terms of computational power on the gateway. In terms of rule configuration, the solution has the ability to leverage the device shadow. So that is, let's say, a solution for a local repository of the rule configuration on Greengrass. This was a design choice based on the lack of any other options being provided by Greengrass. So Greengrass does not have any general purpose storage mechanism being used by Lambda functions. So basically, we went through the device shadow document as an embedded capability of AWS IoT and being supported by Greengrass for the rule configuration. And this is also interesting because with the shadow mechanism, we can replicate shadows documents from the cloud and to the edge in both directions seamlessly. This option has some limitation in terms of rule size because the device shadow document has an upper bound limit of 8 kilobytes. And if we look this in a more comprehensive way, we have basically to cope with this limitation in order to accommodate the needs for rule configuration, as well as for other device-related state information that are stored as part of the same shadow document. And this limitation in the context of the rule execution will pose a limit to the number of rules that can be configured and the average size of a specific rule configuration that should be accommodated within the 8 kilobytes. Okay, so coming to the conclusion, I think that after this summary of the architecture of the use case, we can summarize this with conclusion from both Enel and the AWS perspective.
Okay, from Enel, the key takeaways from the project is, first of all, that we have this convergent IoT platform, meaning a platform that we can use to build a customer solution from the very big industrial customer to the retail consumers that we have. Secondly, we have trained all of our development teams, the different, what we call solution centers and the different system integrators on how to develop solutions on top of this IoT platform. We have also defined what is the governance model for the IoT platform evolution because we know that this is just the beginning. So we are going to need to evolve this platform to incorporate new capabilities. So there was a good amount of work put into defining this governance model. And then finally, with this solution, we think we are ready to use IoT to transform the use of energy.
Okay, and from AWS perspective, I think that the IoT project at Enel was a kind of iconic project in order to introduce and leverage as much as possible the concept of serverless architectures as well as managed service as part of the architectural design and implementation. So we have, as I described as part of the solution, we have tried to use Lambda function as well as embedded capability of the different services as much as possible in order to speed up the implementation and make it, let's say, very efficient from a design perspective, but also from an operation perspective. This has also allowed us to, let's say, to optimize in the implementation phase. So the project was able, let's say, to be completed from start to finish, from requirement gathering to the UAT test in more or less 6 months in 2017. And this, let's say, thanks to the capability that we leverage in terms of internal capability that of the service being used as part of the solution. And we have basically, as part of this project, we have also established a very strong relationship with the different service team within AWS organization in order to make this solution being future-proof, in order to accommodate the new services that AWS will be launching, as well as enhancement to the existing service, in order to make this solution being the reference platform for IoT project at Enel across different business units. So I would like to thank you very much for the time spent together as part of this session. And Ignacio and I will be still around in the room in order to answer any question that you may have on the solution that has been presented. So thank you very much for your time.
Thank you.